Hey kids, Smath here. So our next video is on equilibrium constants and calculating equilibrium constants or the equilibrium concentration of a substance, which would be nice to know. So the equilibrium constant is going to be called KEQ. Now we did a K when it was a small k, and that was rates. That just told us how fast the reaction was going. And you saw that when I wrote that I was writing this as a lowercase, that the rate was equal to a lowercase cursive k. Equilibrium is equal to a big block K. All right. Don't get the two confused. We're going to usually put a sub after this that's called a KEQ, an equilibrium constant. And what this is, simply put, it's a ratio of the products over the reactants. Now these are in brackets, so we mean concentration, molarity of these substances that are going to be there. This whole thing has a fancy name. This is called the law of mass action. Never going to ask you that. No one's going to ask you that. But it is a law for equilibrium. Just remember, products over reactants. And in this case, unlike rates, these coefficients of C's and D's, that lowercase c does become an exponent now. So these are real important, and we're going to do calculations with them in a minute. I have a couple of calculations, but just remember products over reactants and use your coefficients. Big deal, we do a calculation, and what does this mean? Well, it means a lot. If the K is bigger than 1, then what that means is the products are going to be favored. This reaction is going to work. It's going to proceed from reactants to products. If it doesn't, if the KEQ is less than 1, then the reactants are going to be favored and the reaction isn't going to proceed very far forward. Does that mean that the reverse reaction would proceed? Yes, that's exactly what it means, is that if KEQ is less than 1, the reverse reaction's happening, not the forward reaction. Okay, now I've got 2 example calculations for you here that I want to walk through. And what we have is at 300 Celsius. Let's take a minute and see, why are they giving us a time? Well, these KEQs are dependent on temperature. So are we going to use that in our calculation? No, but when we solve this problem and say that the KEQ is 0.25, that's only 0.25 at 300 Celsius, not across the range of temperatures. KEQs are temperature dependent. They're reaction dependent. Every different reaction, every different condition has a different value of K. So at 300 Celsius, 1 liter of a gas contains 0.1 mole PCl3, 0.01 mole Cl2, and 10 to the negative 4th moles of PCl5. If one of the reactions is the decomposition of PCl5, what's the KEQ? Okay, so first let's write the equation. PCl5 is decomposing to PCl3 and Cl2. And someone's going to be upset, so we're going to make that a double-headed arrow. It's equilibrium, that's fair. I get sloppy and forget those sometime. So this is our equation. It's a decomposition, and there are no exponents, so we're okay here. Now let's read what our data gives us. It's 0.01 moles of PCl3, 0.010 moles per liter, and the same of Cl2, And the reaction, the PCl5 is 4.1 times 10 to the negative fourth moles per liter. This is all possible because I've got a 1 liter container going on here. So it wants to know what's the KEQ. So the KEQ is going to be equal to the concentration PCl3 to the first over Cl times Cl2 to the first over PCl5. No exponents, no coefficients, so no exponents here. So all we have to do at this point is plug our numbers in and go 0.010 molar, 0.010 molar, 4.1, 10 to the negative fourth molar, and we get a KEQ of 0.25. That's less than 1. So what we would say is the reactants are favored. What does that tell us? Well, it tells us that PCl5 is more stable than PCl3 and Cl2 separately. That if we were to put these two together as reactants, that would proceed very well towards PCl5. Okay, so this is the first type of problem where we're calculating what the KEQ is. Now in this second type of problem, we're going to go a little bit backwards. I'm going to give you the KEQ and we're going to have to calculate the concentration of one of the reactants or products. So a company has an equilibrium constant for the production of ammonia, and it tells us the KEQ is 580. That's a big number. So that tells me that when I put N2 and 3 H2s together, this is going to make ammonia. It's going to proceed towards the ammonia side. So it asks us which direction is favored. No problem. Products are favored big time. Okay? Now what it wants to know is what's the concentration of ammonia? That's my question. If nitrogen. So here's what I'm going to do. I'm going to rewrite this down here. 3 H2s gives me 2 NH3s. And it says the concentration of nitrogen is 0.70 molar. The concentration of hydrogen is 0.12 molar. That's what we're looking for. So the KEQ in this case would be equal to the concentration of NH3 squared over the concentration of N2 times the concentration of H2 cubed. Now we have coefficients that come into play, and those are pretty important. So we know the KEQ is 580. That was given to us in the problem, is equal to the concentration of NH3 squared over the N2, which was 0.70, times 0.12 cubed. You can plug this into NSolve, you can cross multiply and take the root. It doesn't matter. What we find out is the concentration of NH3 is going to be 0.84 molar. Plain and simple, use the KEQ to calculate the concentration of one of the reactants, or in this case, the product. These are KEQs. These are KEQs. These are equilibrium calcs. I'm Smath. I hope this video helped you.